Single Displacement Reactions and the Metal Activity series. So a single displacement reaction is when you have one element replacing the other, and so their generic way of looking at them is you'd have something by itself, and then you'd have something in the form of a compound, or at least written down as a compound. It may be dissolved in solution, so it may be separated, but it'd be written down in your formula like a compound would be. And what's going to happen if the reaction occurs is that one of them will replace the other, and they will replace things that are like them. So if A is like a metal and B is like a metal, that's where the replacement is going to be happening. However, if A is, say, a non-metal, then it would be replacing the non-metal, as we'll see at the end of this, in the particular compound. Once you do that, in this case, B will now be by itself, and now A and X will be making up the compound. Some things to note is that, again, this compound, if it is aqueous, remember that it's not actually together. The A and X are both the ions in solution, and so in that case, the B would be by itself now. It could be doing that as a solid, or depending on what it is, maybe a gas. And the thing that is being written as a compound could, in a lot of cases, will be aqueous. In order for, let's clear this up a bit. In order for a metal to be by itself, it's going to have to be a solid. So, for example, if A were the thing that was by itself, if it was some type of metal, we would be finding it as a solid. And if it was reacting with BX here, as mentioned earlier, it would be aqueous. Then, if this reaction were to occur, A is going to replace B. So now B, if it's going to be by itself, and if it's a metal, it's going to have to be a solid. And then A would now be in solution with X. There it is written out slightly better. The metal to be part of a compound. So again, here it is as a part of a compound. On the left-hand side and the reactant side, B is part of the compound. And on the product side, right-hand side, A has switched out for B. And so they would have to be aqueous in both of those cases. So metals, when they're by themselves, are solid. And when they are in part of a compound, they are aqueous. And with a single displacement reaction, we see them switching places. So again, this gives you an idea of what's actually happening behind the scenes there. How would a metal go from being a solid to being part of a ionic compound that is dissolved in water? The answer is in the electrons. So again, example here, if we had sodium, if it's going to be by itself, it's going to have to be a solid. And then if it's going to be reacting with lithium bromide, the lithium bromide would be in solution. Reacting two solids isn't going to work. You need to be able to have the particles react with each other, bump into each other, and the only way that's possible is if the ionic compound is dissolved. The lithium bromide is aqueous. So if this reaction takes place, we'll end up with the lithium now being a solid, and the sodium is now part of this compound. But remember, if this is aqueous, they are not actually together. Those two ions are separated from each other in solution. Now the question is this actually going to happen? Is this reaction going to occur? Probably to this point you may have assumed that it's a single displacement reaction. This is what would happen. But the question is, will sodium actually be able to replace lithium? And for that, we're going to be using the metal activity series. Side note, hydrogen is going to be treated kind of like it were a metal. We know hydrogen is definitely not a metal, but it does form a positive cation. And so it, just like metals, it can be found in compounds as a positive cation. So these positive hydrogens. And then when it's by itself, it's going to be found as H2. It's a diatomic gas. So we'll see that along with the metals. So for example, if we had zinc reacting with hydrochloric acid. So again, if the zinc being a metal, it's going to have to be, if it's by itself, it's going to have to be a solid. And in this case, hydrochloric acid, as with all acids, are going to be aqueous. And notice that we don't have a metal per se in hydrochloric acid, but we do have this hydrogen ion, which is a positively charged cation. So if the reaction is going to occur, it'll be the zinc replacing the hydrogen in HCl. If that happens, the H is going to be by itself, but being as it's hydrogen, it is diatomic when it's by itself, and it is a gas. So if a metal displaces hydrogen, then you form hydrogen gas. And the zinc is going to take its place with the chloride, but of course zinc's charge is 2, so this will be ZnCl2, and this will be aqueous. And you can't leave that as it is. We have to make sure the equation is balanced. So if you drop a 2 in front of your HCl, you now have the balanced chemical equation showing the displacement of the hydrogen by zinc. Blue on blue is not a good color choice. So the zinc replacing the hydrogen, and now the hydrogen's by itself, and the zinc is, again, the way it's written, you think it's part of the compound until you remember that it is aqueous, which really means you have zinc ions surrounded by water molecules, and you have 2 chloride ions per zinc ion also surrounded by water molecules. So these single displacement reactions might occur or they might not. They will not happen, and we can write no reaction to say that they're not happening, if the metal, or hydrogen, when it's by itself is lower down on the activity series. So this brings up what is the activity series. So the activity series of metals and hydrogen is a ranking of the different metals' reactivity. So essentially, by experiment, we can figure out who can displace who in a single displacement reaction. And if you rank them all and you put them in a list, you put the most reactive at the top, the least reactive at the bottom, you end up with the activity series of metals, or just the metal activity series, depending on who's talking. It's essentially a list of which metal ions can take electrons from which other metals and become solid. Because if you look at a single displacement reaction, that's really what's happening. You have a metal that has electrons and you have a metal that doesn't. And if they switch spots, they can only do that by taking and giving electrons. So your metal activity series, or activity series of metals, is this list right here. And lots of different forms for it, but essentially it is a list of, as you can see here, metals, and the most reactive is at the top, the least reactive is at the bottom, and this tells us who can displace who. So if you have a solid metal that is higher up, it will be able to displace any metal that is below it, and we'll find those as ions. So for example, if we have, let's say, right at the top there, lithium, if you have lithium as a solid metal and you reacted it with something else, and let's say it's something with a chlorine that's aqueous, the question is, will that reaction happen? Will that be a single displacement reaction? And as long as you have anything below lithium, so let's say, I don't know, calcium. So if this was calcium chloride, lithium, being higher on the list, can displace the calcium ion, and that would form calcium by itself as a solid, and we'd end up with lithium chloride now as part of the compound, which is really aqueous. Of course, we want to make sure that we balance that, and so we put a 2 there and a 2 there, and then we have our balanced chemical equation. However, let's look at the opposite situation. Let's say we had calcium by itself, and we reacted it with lithium chloride. So the question is, will that happen? Will we actually get some products here? And let's look at the numbers. Let's go purple here. So we have calcium, and calcium's trying to displace lithium as an ion. But as you see, lithium is way up here at the top. Calcium cannot displace anything above it. So this will be no reaction because calcium is lower down than lithium. Lithium can displace calcium, so you do get a reaction happening when lithium is trying to replace calcium. But if the opposite were to take place, if you tried to get calcium to replace lithium, it would not. You would get no reaction, again, because calcium is lower down than lithium. Calcium cannot displace lithium, but lithium can displace calcium. So what we end up with is being able to apply these and figure out which reactions will happen, which single displacement reactions are going to happen. If we have iron as a solid, remember the metals, when they're by themselves, they will be solid. It could try to replace copper. In this case, we have copper sulfate. So the question is, will this happen? and we look at our metal activity series, we find iron on here, so there's iron there, and we look at where copper is, there it is down there. Since iron is above copper, the reaction is going to take place. So iron can displace copper, and if it does that, we're going to see that the reaction will take place. This iron is going to displace the copper. We do get a reaction, so then we write the products, and again, we have iron sulfate as our compound, though it is aqueous, and we have now copper by itself as a solid. Do realize that when you're taking something like any multivalent metal and you're turning it into an ion, if it's going to become part of the compound, you're going to have to decide which charge to use. Is this going to be iron 2 or is this going to be iron 3? I have used iron 3 because if you look at your periodic table, when they give you the multivalent charges on your periodic table, whichever one comes first is normally the most common, the easiest one to form, and so that's going to be the one that you should be picking if it's a multivalent metal. Let's try this one out. Silver as a solid by itself is trying to displace the metal calcium. So if we find silver on our table here, it's down fairly close to the bottom. Calcium is quite high, so silver is trying to displace calcium, and that is not going to happen. Calcium is above silver, so therefore silver cannot replace calcium. So this reaction will not take place. Silver is below calcium, therefore it's less reactive, therefore there is no reaction. And so we can just write no reaction as our products. We will not actually get any products. Notice which types of metals are down at the bottom, and their ability to not react is seen in how we use these metals. So 3 more to try out. Again, if the reaction happens, you want to make sure you write what the products are. You want to make sure that you can write a balanced chemical equation. If there are no products, then if no reaction takes place, then you just write no reaction. So try these out using your metal activity series. You should find that, again, iron and aluminum. Iron is here, and it's trying to displace aluminum, which is above it, so that is not going to happen, so we get no reaction. This second one here, if we thought about it, we have nickel here, and nickel is trying to displace nickel. Now, of course, nickel is nickel, and so essentially that's like saying nothing's going to happen, right? Nickel is not going to be able to take any electrons from itself, and so you're not going to have nickel displacing nickel, so another way of saying no reaction. Third one, we have zinc trying to displace hydrogen, and so yes, hydrogen is not a metal, but you will notice that it is, there's zinc there, and there's hydrogen there. Hydrogen is on the metal activity series. It can act as a positive cation. And since zinc is above hydrogen, you do get a reaction, and we'd form zinc sulfate. And again, when hydrogen is forced out of the aqueous solution, forced out of the compound here, it's no longer going to be an ion, and it will actually form H2 gas. Magnesium is above tin, and so again, we have our magnesium, we have our tin, so magnesium can replace tin, and we do get a reaction producing magnesium chloride and tin. The halogens also have a metal activity series, and you don't need it to be given to you because it is the order in which they come on the periodic table. So if you look at the halogens, the one that's highest up on the periodic table is the most reactive. So fluorine is more reactive than chlorine, which is more reactive than bromine, which is more reactive than iodine. So if you want to write it as a column, that is how you see it on the periodic table. And again, most reactive is at the top, the fluorine, and least reactive is at the bottom, the iodine. So anything above can displace anything below. And again, think about what you know about atomic structure, what you know about what's happening as you move up the column in the halogens in terms of atomic structure, and it should make a lot of sense why fluorine would be more reactive than iodine. So let's say fluorine tried to displace, and again, you got to watch out for this. We have a halogen. It is not going to try to replace the metal, right? It could not take its place. You would not form fluorine chloride or whatever that would be. What it's going to try to do is it's going to try to replace the other halogen in the compound. And then to see whether that will happen or not, think of the metal activity, the halogen activity series, the order in which they are in the periodic table. Since fluorine is above chlorine, fluorine will be able to replace chlorine, and we will get our reaction. You want to make sure that you write the products for it, and then again, we're forming diatomic. When chlorine's by itself, it's going to be diatomic, and make sure you balance the chemical equation. And there is our activity series for both metals and for halogens.